got is a selection guide that we have, which is there to sort of give you, a selection of which valve's going to be working best on one application. Now, it isn't designed to be a sales presentation, so please don't be expecting me to ram Metso down your throat. You'll actually be seeing photographs of other control valve manufacturers and actuator manufacturers on here. So it isn't designed for that. It's more about information, for me to try and pass on my experience as we go along. Now, the presentation is going to run for an hour and 30 minutes, so hope you can cope with that. So if you've got any questions as you're going through, please ask. I do have a few additional slides if anybody wants to see them, to do with steam conditioning, but I'll leave it to the end because I'm conscious, if you like, that people have got time constraints. So, if you feel you want to see that a little bit, we can put it in. It's quite simple for us to do that. Okay, moving on now. The first one is going to be your globe valves. Now, globe valves have been traditionally accepted as the mainstay for most control valve applications. So wherever you're going in industry, whichever plant you're going to be going on, you're going to see loads and loads of globe valves around there. They've been there for years and years, and historically they've done a really good job. So they're good for general purpose solutions. Now when you see them, you're going to see them in three forms. So the first one is going to be the standard format. So here you've got your globe valve body, and then you've got your actuator. Now globe valves are sometimes referred to as linear valves, and that's because the action is a sliding stem to lift them in and out. So here you've got your globe valve, you've got your linear actuator, which is a diaphragm in this case, and then you have your positioner on there. I've got a little valve I'm going to be passing around in a minute, so you can actually have a look and see what one looks like on the inside, and then you understand what I mean. So here's where they come in really, because they're a wide size range and a wide pressure range. These things have been around for ages, so they've been designed to do all applications. So 1/2 inch up to 24 inches, typically the kind of sizes you're going to be seeing your globe valves. But what you don't want to be doing is buying 24-inch globe valves unless you have to, because they weigh absolute tons. So just massive things. So here's where I'm suggesting think about different options when you're doing your valve selections. So typically flanged or weld ends. The weld ends you'll tend to see predominantly going to be in the power industry. So if any of you are working for the power plants, you'll see them all there on the that side of it. But normally they're always flanged. So pressure ranges are going to be from ANSI 150 up to ANSI 4500. Now some people might think ANSI 4500 is quite a high pressure, but if any of you have been working on polyethylene plants, then the reactions are taking place at sort of 3000 bar. So you have to have control valves that are going to operate in those sort of pressures. So here are some of the other connections you can normally have. So you've got your flanged, you've got ring type joints. You don't traditionally see many ring type joints. The ring type joint connections are normally going to be in gas plants and this sort of thing. So it isn't a standard thing you're going to be coming across, normal. You used to see screwed valves when you were dealing with utilities, if anybody's doing any heating and ventilating work. But nowadays most people stay with the connections. Then obviously you butt weld end in your power. A very wide material selection. Because these valves have been around for a long time, they've been used for everything. So Hastelloys, Manels, chrome mollies, all of these things are going to be out there and available. So it's just down to how much money you want to pay and where you go. And then you've got various trim options that come with the valve. So quick opening, which is an old one if you like. You used to see it for self-operating control valves, but nowadays you don't see many self-operating control valves. And then your traditional ones are linear and equal percentage characteristics, which are standard. Here's where globe valves come into their own. Low noise and anti-cavitation technology is far excels anything you can do in a rotary valve. But we'll cover that in a section at the end where we've got an extensive coverage there. And also here, high pressure drops. You can be doing 160 bar pressure drops on a globe control valve. It won't bother it whatsoever. You try that on a rotary valve and it will shake itself to pieces in a matter of hours, sort of thing. Limitations on globe valves has always been down to the turn down or rangeability. So is everybody familiar with rangeability? Everybody understand what that is? So I like to think of it as if you like to split the flow into a ratio. For instance, if you've got your maximum flow, you can split it down to a 40th and still get control. So you have to size a globe valve to be bang on. So normally we try and size them to about 70% open. If anybody's offering you a globe valve sized at 50% open, you're already running into trouble because you're running out of rangeability there. So always be careful here. And the other area where you need to be careful with globe valves is if you're dealing with a very light hydrocarbon, for instance, then the gland systems are never particularly good, because as the valve is opening, the stem will actually drag the products out with it. So what you end up doing, you end up putting bellow seal bonnets on. Bellow seal bonnets cost a lot of money, and they're very limiting in the number of cycles you can have. So here are the three forms. Standard globe valve. Occasionally you're going to see an angle globe valve. You're only going to see the angle valves on the more aggressive applications, the specialist applications, which we'll talk about in a minute. And then also you'll see them on three-way valves, where you might be doing a job which is going to be involving heat exchangers, or maybe you've got tanker loading systems. So those are the sort of things you're going to see them on. So moving forward to what's actually going on inside. So if I pass this little demo valve around, so the valve that's coming around is what's called a top-guided unbalanced control valve. So the idea with this valve, if you like, is the flow will come in underneath, and then the plug is just a plug, so it's like a piston. So whatever pressure is acting on the underside of the plug has to be taken care of by the actuator. So you have a limitation there, and then the flow will exit through the valve and come out. So it's not as heavy as it looks, it's made out of plastic, so it's nice and light. So if you want to pass that one around as you go. Now, here we've got the new designs of valves, but here we've got the old-fashioned designs of valves. Now, I'll leave this in my presentation because when you go around a refinery, you'll find hundreds of these things, and the actual refiners love them. The reason being is it's very old, it's very simple, it's very robust, and it's maintainable. Now, as a manufacturer, the idea is, if you like, you want to make it simple, cheap, and economic to manufacture. But by doing that, we've then brought limitations in. So you have to weigh up the limitations now versus the old technology. So here you've got, this thing's called a top and bottom guided. So basically what you've got is you've got your plug here, and then you've got bearings at the top and bearings at the bottom. So the plug is actually supported in those bearings as it's riding up. So your flow will come in, and in this one, which is a double ported design, the flow will exit through both sides like so. So double porting gives you a balanced construction, so that means now you can have a large valve with quite high pressure drops and still keep quite small actuators. So it's quite novel. Now the limitations, if you like, in the design is that these things use screw-in seat rings, and you'll get, when the valve is actually shut, you'll get leakage going around the sides of the seat rings, which will wire draw the body. So although it's robust, it will still have a maintenance issue. But the reason the refiners really like these is that these valves will tolerate all manner of crud. So if you've got a lot of coke in your process that may be coming through, if you're dealing on the distillation side of a refinery, for instance, then the crud doesn't bother this valve. It will just pass through it without causing any stiction in the valve, and the valve will keep working for years and years through the maintenance cycle. So this was sort of like the king for years, up until about 30 years ago, and then they started to bring in the new designs, which are the cage guided or cage retained valves, which is the valve that's actually being passed around at the moment. So on the valve you've got coming round, it's this one here, which is an unbalanced valve. So here your flow will come through, and then it will come up through the port. Here's your plug. The plug will have a contour on it to deliver your characteristic, and then the flow will then exit through this cage here. And then you've got a guide at the top which supports the whole thing. So this valve in its form is capable of being used on dirty fluids like hydrocarbon, but because it's an unbalanced construction, you're limited by your pressure drops, because you need monster actuators for bigger pressure drops. Now, the reason these valves were sort of designed like this is that you could have a valve body which would be simple. So literally you can remove this cage and you can replace it with all different sizes of trims, all different sizes of plugs. So it then becomes a one size body with all different options inside it. Whereas with the old style of valve, you only get one option, and that's what it is. So here you can see you've got the standard plug. Here you've got what we call a microform or a microflute trim, which will be a very, very small trim, allowing you to go down to quite small CVs. And then on this side you've got what we call a balanced construction, and what this is that instead of having a plug which just has the pressure applying on it, The flow comes in now from the top through into the trim, and then here you've got the plug is like a piston in an engine, so it rides up and down in the cage. But you've got drilled holes here which are balancing. So basically what happens is whatever pressure is on the inlet is also on the top of the plug. So now it means you can put really high pressure drops on there, and the only unbalance is going to be down to the diameter of the stem. So here you can have maybe 10-inch, 16-inch valves and still have, you know, quite large pressure drops across them. The only trouble with the new design like this is if you're on a refiner application, for instance, then because it's like a piston in an engine which is highly toleranced, then any grits or residues that may be in the flow are going to cause stiction. So be very, very careful if you're working on larger glow valves in a, you know, hydrocarbon environment, because you're likely to get stiction if you're using this design of valve. So just be careful what you're doing. Always use the unbalanced if you can, but then you've got the limitation of how big your actuators are going to be. What we've got here is a three-way valve. Now the three-way valves are basically an offshoot of the old-fashioned design. So basically what will happen here is that where you've got what we call the blind flange at the bottom, which holds the bush, we remove that blind flange and now we fit an actual flange. So basically what you've got now, you've got this sort of construction, but you've got three ports. So you can buy them in two forms. You either have them as converging or you have them as diverging. So here we've got a converging one where the flow will come in like so. On the other hand, if it was diverging, your flow would come in this way and then be going out there. The reason you have the two is that these valves are traditionally always used for heat exchanger applications, and some people like to fit them downstream of the heat exchanger, in which case it's a converging flow, or some people like to have them on the upstream of the heat exchanger, which is a diverging flow. So you take your pick. I think the only time you'll be using the diverging flow in a different application would be on something if you were doing a tanker loading system, where your flow would be coming straight through the valve, and then as you open this port it will allow you to discharge the flow into the tanker. So that's when you will be seeing that sort of construction. Now moving forward to the angle valves, as I say, you won't see these very often. They tend to be for very specialist applications. So here we are talking about applications where you might be looking at compressor anti-surge valves, high pressure gas letdown valves, wet steam letdown valves, boiler feed water control, where you'd need multi-stage trims. Now with angle valves, you've got a sort of two ways of using them. If you're going to be using them on a gas application, for instance, the key factor within a valve on a gas application is going to be velocity. Because normally on a gas application you're talking about noise, and within a noise application you've got to keep the velocity down to 0.5 Mach. So what they will do on a gas valve, your flow will be coming in from the underside. So typically here, if you like, you can get different sizes of bodies and trims. So an application I'll give you is one that I did about 2 years ago for Valero Refinery, where they were looking for a valve on a wet gas compressor. So basically what you've got a 16-inch outlet. You've got quite a high pressure drop, which was then discharging to flare. So to keep the velocity down, they ended up making the outlet a 24-inch outlet. So you basically fabricate the valves to suit all of these different combinations. So if you're talking a gas application, then velocity is the key. So you've got these options to consider. Now what you'll find on a glow valve is, to keep the velocities down, you end up using bigger trims, because the trims, if you like, on a noise valve are made up of all little holes drilled in there, so they limit the capacity. So you end up with relatively small flows, but sometimes quite big cages to give you that velocity you need. Now, if you're working on another application then, which might be a difficult one, shall we say wet steam, then wet steam is extremely erosive. So instead of running it the normal way, where, for instance, if you've got wet steam, you'll be discharging the wet steam into the body of the valve, wearing the body of the valve away, then what you will do then, you will bring the flow in from the horizontal side, through the trim, and then discharge the wet stream straight out. So basically what you're doing then is, where the flow stream ejects the valve, it's ejecting straight out, so it's not wearing any of the castings or wearing any of the bodies away. So it's a simple construction to do. And if you're looking at applications where you're looking at multi-stage trims, then what they will do, instead of having a single trim here, you will have multitudes of trims coming down below. So I think Fisher do a Cavitrol 4, which is like 4 separate stages coming down, and that will allow you to drop 160 bar pressure without sort of generating cavitation in the trim. Now, just looking at your trims themselves, they're all characterized by the different profiles you'll see on the base of the trims. So here you've got your equal percentage, which is your normal characteristic for things like pressure control, flow control, temperature control. And here you've got your linear, which is what's going to be in there for level control applications. Now, some of the manufacturers came up with this wonderful idea of doing modified equal percentage, which is kind of a halfway house. Excuse me sitting down, I've got a trapped nerve in my back. So the manufacturers came up with this idea, and it was like a halfway house. So once again, it meant you could have one valve that would do all different applications, if you know what I mean. It's a bit of a cheat, but you get away with it. But what you'll find is that most people will specify these trims, if you like, for the applications, because that's what's traditionally been used. I mean, the history of the characteristics is going down back in the ages when you used to have pneumatic control systems. So when I used to start, you used to have a blind controller, as it was called, which was just downstream. It was the old Fisher Wizards. And they used to measure the pressure, and then to get the right sort of performance of control, you had to modify the trims, modify the characteristic to deliver what you want. In the modern DCSs now, you can do basically what you want with any of the trims just by doctoring the output from the DCSs. But we like to stay with tradition. Now, when you've got the cage-guided valves, then which is the balanced construction, then the actual characterization is done by profiles which are actually in the cage of the valve. So here you can see a linear characterized cage, so you've got this linear profile here, an equal percentage characterized cage where you've got this rather strange curvature here, and then a quick opening one, which is the kind of trim that you've got in my little demo valve that's been handed round. So that passes on from the globe valve side. So the next section we're going to be talking around is butterfly valves. Now, butterfly valves, I believe, have been quite misunderstood over the years, because originally when they first came out, salesmen were selling them for all manner of applications, whether they were right applications or the wrong applications. And the reality was they got a really bad name about 25 years ago, and people started, I'm not buying them because the control is rubbish. But if you buy a butterfly valve which is selected for the application, then you get a unique thing, because you can have really large sizes of butterfly valves, that weigh half the weight of a normal globe valve and are like a third of the cost. So there's a large amount of money to be saved by considering using butterfly valves, providing you select them for the right application. So they're available in various forms. Some are for control and some are for isolation. Good for general control, but here's the buzz, if you like. You've got to be careful with the pressure drops. Now, some people will tell you can handle 10-15 bar pressure drops on a butterfly valve, but my gut experience is just to stay around about 5 bar, because what happens with butterfly valves when they're working is you get turbulence forming around the backside of the disc, and those turbulence then will cause oscillation, which will then be reflected in the control. It will also be reflected in the maintenance levels of the valve, because you'll start to shake the valve to pieces and wear it out. So just be careful when you're looking at a butterfly valve. If you've got an application on flow control, which is a big line, maybe 10, 15, 16 inches or 20 inches, butterfly valves will give you a really good solution and they'll be extremely reliable. But you need to pick and choose them for the application. They're available in what we call wafer form, which means they will actually be bevolted between flanges, so not ideal for an application where you might be dealing with a volatile liquid. On the other hand, you can buy them with lugs. Now the lug construction is basically where you will have holes which will be drilled and tapped around the periphery of the body. So when you bolt them in the line, you screw in studs and then you can clamp up and you'll get a good connection there. And usually the guidelines are you can use a lug valve on a flammable process anything over about 8 inches, because you're going to get a good face-to-face there. Or better still, you can go with flanged and occasionally weld end. So you haven't got any of it around here, but in the areas down in the Derbyshire and Nottingham area, they have a lot of what we call district heating systems. which is sort of like hot water which is pumped all around the cities. You might have them in Newcastle. And the idea then is, if you like, they bury this lot underground, so they can't afford a flange, they can't afford a leak, so the valves will all be weld end. Now we've got single, double or triple offset in butterflies, so I will explain that to you on the next slide, which sort of talks about it all. And then we've got very high flow capacity, so in comparison to a globe valve you're probably looking at what, 3-4 times the capacity for the same size. But here's the king that people get surprised about. The turn down on a normal butterfly valve is 60-1 with a control actuator. So immediately, if you like, the control performance of the butterfly valve is ahead of a globe valve. It just has its limitations. So hence, when we started off, think about your applications and think about where you can use a butterfly valve instead of a monster globe valve. Temperature range is -196 to +800, so you can go all the way through whatever you want to do. And they're also pretty good on severe surface applications as well. So high cycle, if you're dealing with slurries, I do a huge amount of work on brine, where you're dealing with crystals, and they last for years and years with no issues, no gland leaks, no problems. So crystallizing media, and also vents. So if you've got anything where you might have a valve to a flare, then these things will sit there and open on demand when you want them to work. And here's the other thing as well now which is coming in. If you think about what we said about the globe valves with the rising stem, where you're going to get product coming in, you know, being drawn out with the stem. With a rotary valve, it's a little bit like your engine in your car. You very rarely get leaks from your engine nowadays, where you're always going to get leaks from the linear sort of side of things. So it's a simple option. So I'll pass this valve around now. The valve I'm going to be passing around is a triple offset butterfly valve. Now, when you're having a look at it, have a look at the actual contours on the disc, because it'll help you understand how the process works when we start talking about it, you know, as we're going through the slide. It's a little bit heavy, sorry about that. Right, now the original butterfly valves are what we called conventional disc. So here you've got a standard disc, and basically what the disc is, it's just like you know, a straight, simple form. Thank you, cheers. And then you'll have the shaft will be central to the disc. So as the disc is actually rotating, it rotates centrally to the shaft. Now, on your original butterfly valves, which are being used on the likes of dampers and things like that, there was no kind of a seal on there. So where the problems started to come in is that somebody came up with this great idea to fit rubber liners onto valves. And to a degree that was the kiss of death once they started to do that, because it caused that much problem. They've overcome it now because they're now sensible in where they use them, but originally it was being sold for everything. Now, using this technology, to get a shut off, they had liners here, and the liners were normally made of things like neoprene or bitons, this sort of thing, like a rubber. But with the rubber came a temperature limitation, so you were looking at typically up to 150, 170 degrees C before the liner became hard. And it was a harder line, you know, liners becoming hard, which started to cause a lot of the grief in the old days, because as the valve turned, it would literally rip the liner out of the valve, and then your valve would be a total failure. So the manufacturers came up with this great idea now to change the design so they could actually start to increase the temperature capabilities of the valves. So now we went to what was called a double offset. Now, by double offset, what you've done, you've moved the shaft center from being central to the disc now to offset. So it's offset on the horizontal and it's offset on the vertical. And what that does for you is, as the valve is actually stroking, it now means as it's closing in like a camming action rather than just a straightforward rotation action. Now, that camming action then allowed you to start to use harder materials for the seals. So seals like nylon started to come in, and seals like stainless steel shims started to come in. So what it did then, it didn't affect the control performance, but it now allows you to take the temperature ranges up to plus 250, up to sometimes up to plus 400 if you're on a metal seat. But once again, because of the shim seals, if you were dealing with things like steam, the shims started to fracture and give you grief. So then people came up with this great idea of triple offset, which is the design of valve which is coming round now. Now, the triple offset uses the same disc sections as you've got here, where you've got the double offset, so it's got there. But the actual profile of the disc, instead of it being a circular disc, it's now a section through a cone. So if you look at the edges on the disc that's coming around on the valve there, you'll see that one edge is now virtually square and the other one is quite tapered. And the actual surface of the disc is more of an elliptical shape rather than a circular shape. So what that means now is we can now use extremely hard seats. So the seat you've got there is almost like solid lumps of metal. So with that, if you like, now you can get bubble tight shut off on temperatures up to 600 degrees centigrade, and also you can get extremely good control. So this is sort of like the evolution is your butterfly valves as you're going through. So if somebody's talking to you about the triple offsets, at least you'll be able to understand a little bit more now as to, you know, what it actually means and what it's all about. Moving forward again now onto ball valves. Now a lot of people don't normally consider a ball valve as being a control valve, but we supply large amounts of ball valves on control applications because, you know, when this thing is open, it's a full bore pipe. So size for size, you can have something that's sort of like a third of the size of a monster glow valve and still give yourself good control. Now the key issue is that you need to be careful about the drive mechanisms, because if you think of a normal soft seat butterfly valve, it has a very crude linkage on there that might have something like 5 degrees of deadband in that linkage. So in a control application, you might find the actuators moving 5-10 degrees, but there's no actual change in control in the valve. So we don't normally consider a soft seat ball valve as being a control valve, but when you start to look at the metal seat valves, then they will come with spline drives and keyway shafts. So now you're looking at virtually zero backlash in the linkage systems. So now you've got all different kinds of options to consider, because I don't profess to use these as a normal everyday control valve, but I do a lot of work on the refineries and so on where we might be debottlenecking a plant. So if you've got a plant which you need to debottleneck, you can either rip it out and start again, huge amounts of money. On the other hand, if you can put a valve in that would replace your glow valve without any changes, then immediately you're going to be delivering another 60% capacity but with no change. The pipe work has normally got the capacity in it, but the valve normally hasn't got the capacity. So when you get applications where you might be thinking of doing a change, don't just sort of think, write it off, I can't do it. Consider using a ball valve as an alternative to you know, changing everything around. I've done it many times. An example, the Valero refinery, they were debottlenecking the furnaces into the atmospheric distillation unit. Large amounts of money involved, because effectively they got all the valves running flat open and they got the bypasses open to try and control. So they put a valve in here which is it's a reduced bore ball valve, but it's a glow valve face to face. It delivered another 60% capacity. Now that immediately overcame the problem of the lack of control, but there was another spin-off that came in afterwards as well, because they then found that where normally they would have to clean the furnaces out after 4 years, there's so little pressure drop in the valve, they can now run the system for another 4 years before they're cleaning the furnaces. So a simple selection of changing from a, you know, your standard glow valve to a rotary valve has delivered, you know, huge amounts of profit and minimising service. So consider all the options. Here you go. So great for debottlenecking. If anybody's in the paper industry, they use a lot on paper stock, which is almost, if you've got a bucket full of paper stock, it won't come out if you tip it upside down. You can handle that kind of stuff with it. Tight shut off if you need a valve to be a sill valve as well as a control valve. But here's the rubber's end. Rangeability on the ball valve is 80 to 100 to 1. So now you're looking at sort of double the capability of a glow valve for control, so you can get extremely sensitive control on them. And very good on severe service if you see them. And with some of the valves as well, you can get them with noise and cavitation trims, dependent on, you know, which manufacturers you go for. I put this one on just out of interest. Anybody do any work on crackers, anything like that, where you're dealing with catalyst handling systems? So ceramic ball valves, all the internals here are made out of zirconium silicate. So if you do have any applications where you're dealing with extremely abrasive things, don't just put something in you've got to keep servicing every 6 months. Consider a ceramic ball valve, because they'll give you really good control, but they'll tolerate all manner of crap and horrible stuff. And as you can see here, minus 70 to plus 450, so they're going to cover most of the applications that you guys are going to come across. Next one is the segmented ball valve, or B-ball valve. I'll pass this one round. Now, the valve itself originates from the paper industry. Now, most people think it should stay in the paper industry, but I find that these sort of valves are extremely useful for a lot of different things. But once again, you need to select them. Now, by segment, basically what it is, it's a quarter of a ball. So where you would have a normal ball valve, which would be a solid ball with a hole through it, this thing's only a quarter of a ball. Say within the paper industry, the idea of it is that you can handle paper stock and control, and it won't be bothered at all. It will just shut off and open up. Nothing gets stuck, nothing gets jammed, and away you go. But say you can use them for other things as well, because they're extremely good on steam. They're extremely good if anybody's doing any work where they want very, very fine control. So blending systems and things like this, if you're dealing with any blending systems on any plants, they're extremely good on there. And also I like to use them as well on gas control systems, because the tradition for a gas control system is you'll have two valves. You'll normally have a pilot control valve. This is, shall we say, for a furnace. You'll have a pilot control valve which is going to be delivering the flow just to keep the thing ticking over, and then you'll have a secondary valve to take it online. Now the problem is when you change it from one valve to the other, you've got a big jump in the actual control side of things. But the other side of it is you normally have to split range these valves, so you're halving the control capability. Whereas if you put something like a segmented ball valve in, these things have got a massive turn down, 150 to 1. So quite often you can do all of it within one application. So very, very flexible. We also do versions of these things which are called basis weight valves. This morning I saw a customer, and they have an application where they have to control the flow of they have to dilute the paper stock going onto the machine. And you can imagine if you've got paper coming on the machine at 2,000 meters a minute, it's all happening very quickly. So the valves have to be extremely accurate. So you can fit these valves with actuators that will deliver 14,500 discrete steps over a 90-degree rotation. So if you come across anything where you need absolute superfine control, which is something you'll get every now and again, then it's easily achievable by using this sort of style of valve. So I'm looking for my computer and I've got this thing. Okay, next one we've got is rotary plug valves. So these things have been around for many, many years now. They were originally introduced by a company called Mason-Elan. And when they first came out, they brought them out under the guise of the rotary globe valve. And they were extremely successful when they first came out. So people were putting them in all manner of applications. But going back to the thing I said to you earlier on when we started off, you need to select these valves, within the application capabilities they have. So originally people were putting them in for things that they weren't really suitable for, so then they start to tail off then on where they're used, and they start to have problems with them. I think the original valves as well, because Colin used to work for Mason, didn't you, Colin? The original valves were also going to be, if you like, wafer valves, and wafer valves in a chemical hydrocarbon environment are just a total no-no. So they sort of died out. You still see them every now and again, but they're dying out. But they're still available in various guises. So the way that they operate, I'll just hand the little valve around. So instead of it being a ball, this thing's actually got a plug. So you can see here you've got a plug, and the plug will rotate to cover or uncover the port. So that is where you get your actual control capability on this design of valve. So, say originally brought out to replace globe valves. Some people make them in globe valve face-to-face, so you can actually pick and choose for that. You'll see them, traditionally in the chemical industry. They're all over the place in the chemical industry because you're dealing with utilities, relatively simple applications there. But also they're extremely good when you're dealing with hydrocarbons, because the great thing about the valves like this, if you like, is the gland systems are second to none. So where you've got a very hot hydrocarbon, the gland systems are absolutely excellent, so you won't get any gland leaks at all. They'll work extremely well in those areas. So you can buy them wafer pattern, flanged, or short or long. By short I mean the pattern that's coming round, which is the short pattern, or you can have a globe valve sort of face to face. Limitations are going to be on the pressure rating, so you've got ANSI 150 up to ANSI 600 available, but they're quite a wide-ranging valve. And here's why: you've got quite a good turn down on this valve, so it's 60 to 1. I think the thing where it becomes useful is the characteristic of the valve is sort of like a halfway house between linear and equal percentage. So with having a high turn down and that kind of a characteristic, it means you can run the valve, you know, quite securely at sort of 5% open, right the way up to about 90% open. So it's got really quite a flexible range capability within it. So noise trims and cavitation trims are available in these designs of valves. Here's where they come into their own high integrity gland systems. So anybody's got applications where you might be dealing with, you know, hydrocarbons. I mean, one of the applications I bring to mind is we do a lot of work on hydrogen. So 20 bar hydrogen at 400 C, zero gland leaks with a standard valve. You don't need to do anything special around, you know, bonnets or anything like that. So if you've got any tricky processes, worth considering this designer valve because of the gland system. You can also get them fire safe as well, because as soon as you put graphite gland systems in these valves, they become fire safe easily. So wouldn't suggest you use these for all applications, but hydrocarbons or anything where you're dealing with hot oils, you know, thermal fluids, excellent for those sort of things. You'll find a low-cost solution, you know, for a difficult problem. I always put this one in. A lot of people say, why have you got sort of line valves in there? But when you're looking at applications where you might have you know, a very aggressive media, could be you know, carcinogenic or whatever, then you can either put materials in there which are going to be exotic alloys, or you can consider using the line construction for your valves. Now, I wouldn't suggest you use them for all applications, but what I've always found, if you like, with you know, corrosive applications is a few degrees temperature change makes the product extremely aggressive. An example, some years back I supplied a Hastelloy segmented ball valve. It lasted 7 days. And when we found out what it was, the temperature was 8 degrees up on where it should, and it just wiped it out completely. So if you've got applications where you're dealing with really aggressive chemicals, instead of just considering all the expensive alloys, then think about putting a line valve in. So the ones we've got here are Richter. Those are the ones I normally use because they're a good quality. So all the valves, if you've got a ball valve, you've got a butterfly or a globe valve, they'll all come PFA lined, and they'll tolerate all manner of really nasty chemicals. You just have to be careful with the temperature capabilities on line valves, because you're limited up to about 160, 170 before the liners start to, you know, fall down on you. So quite useful to get you out of trouble when you've got some really nasty chemicals there. That ends the section on the valves, so we'll be talking a little bit about the actuators. Now, actuators are going to come in two sort of forms for us, if you like. You've either got your rotor actuators, which are going to be on the top, your rotary valves, or you've got your linear actuators down below. Now, when we're talking about control valves, I like to think about the actuators being control actuators. So quite often I'll get people that are going to be trying to fit a rack and pinion style actuator onto a rotary valve to give you control. But you know, you're on a loss from straight away. It might be cheap, but the amount of lost motion that you're going to find in the linkage systems, the control is going to be absolute rubbish. So always consider your actuators to have a good drive mechanism. We work on the Scotch yoke principles, where basically you've got a piston which will be a linear piston, and then you'll have a double lever mechanism here to give you your conversion to rotary motion. So within the actuators you can either have a diaphragm form, or you can have them in piston forms. So here's the spring opposed piston, the spring opposed diaphragm. Now it's kind of strange really, because when I first started in the business, every actuator was always going to fail open or fail close. And what it is, it's a throwback to the old diaphragm actuators that we used on the globe valves. Now in the paper industry, they want all the actuators to be fail fix. And the reason being is, if you like, if the plant stops, they want the whole thing just to grind to a halt. They don't want to sort of isolate or put something on, they just want it to grind to a halt. So, but people in the chemical worlds and the refining worlds never consider a double acting actuator. But there's some quite considerable benefits, because the actuators are extremely stiff and strong, but there's very little friction in there, so you're not having to overcome a spring. So when you apply air to the top or the bottom, you're going to drive it extremely accurately to the control point. But as I say, if your process will tolerate it, then don't just wipe it out, consider it, because you can save a lot of money on the actuators, and also the size of the actuators are considerably smaller. So here you've got your spring. This is one that's going to deliver you fail open or fail close. This one's your double actor. With the diaphragm sides, quite often you can get them so fail open, fail close, just pull the actuator off and turn them back around and it goes back on again. So you don't have to worry so much then about having a fail open or a fail close problem. If you've got it wrong when you order it, you've still got the chance to change it. So these are going to be things. So you've got your double acting, fail fix, spring open and spring close. So linear valves, then the traditional kind of actuator tends to be a diaphragm style. So here what you've got a diaphragm inside a casing, and then inside here you've got a spring, and the spring will be delivering your failure mode and delivering the power to fail it. Now, anybody remember the term bench set? Okay. Well, when I first started, things like positioners and that weren't available on valves, so what people used to have to do then, they had an actuator with an adjustable spring. So whatever the pressures were downstream, you actually adjusted the spring to compensate for that pressure so that it would stroke 3 to 15 psi over the pressure range that you were working. Nowadays, if you like, people don't have the adjustable springs because they've all got the positioners, and the positioner sort of compensates for that. So this is what your normal diaphragm actuator is going to look like. Occasionally you're going to see piston style actuators. Now the piston style actuators are quite good, they offer quite good control and they're relatively small for the amount of power you get out of them. But what you have to be careful of is some of the piston actuators actually use the air to assist the spring. So if you get anything where the air leaks away, your spring capability to fail in an emergency isn't necessarily going to be matching exactly what you wanted. So although there's benefits from a size on this, sometimes be careful when you're dealing with supercritical applications because you might find you haven't got the backup of the failure mode there. Now actuators are available for electric or electro-hydraulic. So quite often I'll get people that will ask me for electric actuators. And you'll say, well, why do you want an electric actuator? And say, well, it's easy, I've got power, you know. But you have to be very careful with your selections for an electric actuator. So the bottom one we've got here is a standard electric actuator. So you've got a motor here, and then you've got a gearbox inside here, and then you've got limit switches and torque sensors and this kind of thing. And you've got a manual override. It all seems very nice and very compact. But the reality is with these sort of things, if you lose power, the thing just freezes. It stays where it is. Now you can get battery backup systems, but battery backup systems aren't suitable if you're in a hazardous environment, so you can't do it. So you can be in trouble there, so select an electric actuator if it's feasible, but I wouldn't suggest you sort of do it for normal things. If there's no air available, then you're going to be driven down this road. You can get them for linear valves or you can get them from rotary valves. So the rotary one will literally, the gearbox will just rotate 0 to 90 degrees to give you your control mode. But if you've got a linear actuator, sorry, a linear valve on the base of it, then what they'll do, they'll machine a helical bush to the thing, and then they'll have the thing rotating continuously. So what it will do, as it's rotating, then the helical bush will then draw the spindle of the valve up inside itself to give you your linear motion. So it works okay, but you've got a lot of lost motion in there, and depending on what the environment is, you've got quite a big wear point around there, so just be careful what you're doing. So say the fail-safe mode is the tricky bit, but very high power to weight for an electric actuator, so you can have quite a small actuator for a big valve, very good. And also you can get them with all kinds of positioners and limit switches and all kinds of things. But there is one trick with these things which you have to be very careful of, and the actuator manufacturers tend to hide this little bit of information into the small print. Because it's got an electric motor inside here, this motor generates heat each time it starts up. So if you've got an electric actuator and it's on an application which might be cycling quite frequently, quite often you'll find that after a few hundred cycles the actuator will trip out on temperature, and it won't restart until it's cooled down again, which could be 2 hours. I had a major issue with one of my customers calibrating. He was just doing commissioning. It tripped out the commissioning. They couldn't finish the commissioning for ages because every time they tried to start up, it kept tripping out. So be very, very careful about this when you're picking your actuators. Some actuators are available with continuously rated motors, so you can use them, but some of the standard ones aren't, but they'll still be selling them as being a modulating actuator. Now if you want a true modulator, then you'll need to go to electro-hydraulic. So here you've got a hydraulic power pack, which will contain either a pump, or quite often on the smaller valves they'll have like a piston pump, which is like a solenoid, and then it will drive an actuator, which could either be a rotary actuator or a linear actuator. Anybody done any work on Sill, Buncefield, that sort of stuff? These sort of things now are pretty common on there, because you've got a tank farm in the middle of nowhere, you haven't got any air, so they'll put the electro-hydraulics on there to deliver your failure mode for your valves, you know, and it's a secure way. They're still qualified. Rotork, Skillmatic do them, so they're all available for that sort of thing. Positioners are the next one. Now, as I say, when I first started, an actuator on a valve would just be a diaphragm actuator and a valve, and then you'd have a pneumatic controller downstream doing the control. Now, those sort of systems were quite robust and they worked quite well, but dependent on what was going on with the maintenance, or dependent on what was going on inside the valve, then you were in a situation where you might have, you know, friction building up inside the valve. That friction would then mean that the valve wouldn't be stroking as it should stroke. So you might find the valve didn't stroke, you know, its full movement, or it might be moving in jumps. So what they came up with the idea then was to put what they call positioners on. Now, positioners are basically servo devices. So it's a bit like the brakes in your car, you know. You stamp on the brakes now, and your car that weighs 2 tons stops on the threatening bit. The same with these sort of things. So they just amplify, you know, whatever air is going to be in there. So you buy them normally pneumatic, or you buy them electronic. And what will happen on the pneumatics, you will just feed them with the 3 to 15, and then whatever air supply you feed the positioner with, which could be 4 bar or 6 bar, they will then allow the 6 bar onto the actuator to deliver all the extra power to give you control. Now, they always used to be pneumatic, but nowadays it's maybe 1 in 100. Most people now have gone all over to the electronic devices. So here you've got a mixture of electronic positioners. And with the electronic positioners come all different kinds of things now. So you can have them 4 to 20 milliamp, which is your normal control signal, or you can have the digital, so you've got your foundation field bus or Profibus. Anybody done any work on foundation field bus? Kiss of death?
No.
You've been alright, have you?
Yeah.
Yeah, we don't seem to have any problem with the positioners, but the thing is, you've got to have qualified engineers to do everything now. You know, the techies have to be really well trained to work on them.
Big saving, terrific saving in commission. You can commission the whole of your field bus system,
Yeah.
and then start doing.
Yeah, I've got a couple of plants in my area which have tried it, and most of them now have gone back onto analog, because the technicians, they can get normal technicians, whereas you've got to have like IT engineers normally. And for people like us, if you like, you know, we get a phone call, the positioner isn't working. Well, it isn't the positioner, it's the fact that it's dropped off the bus or whatever. It goes beyond normal, you know, technician capabilities to work with. So the new ones come with integral position centers, transmitters. But here's the thing now, which is really good with the new ones. You can get life cycle diagnostics on all the positioners now. So if anybody's on a plant where you're looking to save money and improve the efficiency of the plant, you can now start to analyse the actual maintenance procedures that you're doing, so you can, you know, make it so that the plant is going to live longer, but also you're only going to be servicing the valves you actually want. So quite a lot of information around there. So, and here's the other thing as well, is a lot of people now are asking for the control valves to be part of a SIL loop. So you get all the position as well, which are SIL qualified. So if you're on a sort of an existing plant, you can actually utilise the control valve to aid the SIL system and save yourself some money. So yeah, we've now finished all the valve and actuator side of it. So just a quick flash through here on your rangeability. This is just a quick recap here. So your globe valves are 40 to 1 turn down, butterfly valves 60 to 1, control ball valves 80 to 101, and then you've got your contoured ball, V-ball's going to be 150 to 1, and your rotary plug there. So you can see, if you like, you've got lots of room to manoeuvre to pick and choose what valve you want for the applications. And then here's your characteristics, so you can see just a quick recap on your standard characteristics you've got there. Next section is going to be on noise and on cavitation. Anybody had any disaster areas with any of these sort of things? Nobody owning up? Now I like to think of noise and cavitation basically, a simple term to me, it's like excess energy. In the older world, if you like, quite often you'd have pump systems and you'd have to drop all the pressure across the valve and then discharge it into the plant. Nowadays, if you like, they're putting all these variable speed drives on there, which is alleviating a lot of the problems around here. But you know, we still get these problems, and you still need to be very careful, because anything to do with noise and cavitation can be terminal for the life of your plant. Now, noise nowadays, if you like, when we're doing the valve sizing calculation, you press a button and out pops a noise calculation, so you get your noise calculation. It's all well and good, but you know, I always think it's nice to understand where the noise actually comes from and how to understand it. Now, when I first started, you know, we didn't have all the sophisticated tools. We did the sizing by a slide rule, and at the end of the calculation, you know, you did the calculation, you thought that's okay, but then you thought, oh, I wonder if it's noisy or is it not, because there was no determination from the slide rule. So then you had to do a manual calculation. And what I find interesting about the manual calculation is it puts it into context as to what it is. Now, the numbers for these things are just positives and negatives. So when you start to think about what you're doing, you can understand if one thing's increasing, it's a positive, so your noise is going to go up. So it then gives you an idea what you're going to be finding. So pressure drop, for instance, is a positive number. Flow is a positive number. Pipe thickness is actually a negative number. The thicker the pipe, the more the noise attenuation, so it's actually aiding the reduction of noise. Velocity is a positive number. Lagging is a negative number, because lagging depends on whether you're on thermal lagging or acoustic lagging. They've got different values, and they're all numbers which are taken away from the noise. And then installation, I'll put installation in there because it doesn't have a number with it, but you'll see on the next slide when they give you an explanation just how important it is about that. So here you've got your acceptable limits for noise. So for continuous noise level, you're looking at 80 decibels to 85 decibels. So if you're on a process plant environment, shall we say, which is outside, you know, a big plant, 85 decibels is normally the you know, the limit you want to be around there. On the other hand, if you've got a process plant which is inside a factory environment, then typically they want to keep it down to about 80 decibels. So you need to be careful where you are there. But you are allowed infrequent bursts of up to 102 decibels. So if you've got a flaring situation or a process which may vent periodically, then you can go up to 102 decibels without any worries, and you won't have the neighbours you know, coming on to you. But when I worked for Fisher, one of the guys who was doing the training at the time came up with a novel way of actually explaining noise, because these numbers don't really mean anything, they're just sort of fictitious things. Like 80 decibels is a normal office environment, so if you've got sort of like a receptionist or you've got typists in there, whatever, that's the kind of noise level that 80 decibels is. So when people start asking for 80 decibels, you know, it's nice to put it into perspective as to what you're actually trying to achieve. Now 85 decibels is going to be sort of down the side of a, you know, a road, that sort of thing. So if you're by the side of a, you know, a relatively busy street, that's sort of 85 decibels. 96 decibels is a lady's hairdryer. So, you know, once again, would you want to be in the environment with a hairdryer stuck to your ear 24/7? No, you wouldn't. But at least now it gives you an indication as to what these noise levels are, rather than just having the numbers there, sort of thing. Now, with noise, if you like, we've got two ways of working it. Now, within the valve world, we work on what's called a source treatment, which is we treat the noise at the front end. The idea is we don't want to create the noise, so we treat it at source. On the other hand, if you've had an accident and you've built a plant and then it's really noisy, then you have to go to what's called a path treatment, because now you've got a problem, you've got to fix it. So from the source treatment, if you like, at our end, you've got special trims within the valve, so they're going to be velocity control and acoustic control. Location control is pretty critical. I'll give you an example in a minute of that one. So good piping design, or you can put what we call resistors or diffusers, which are devices which are sort of like fixed orifices. These things are very limited because it's a fixed orifice. They will only have an effect on one of the process, one of the parameters. So if you've got 3 flow rates, it's only going to work on one of the 3. Now, The example I'm going to use to here is a paper mill that was built in Manchester not so long ago. They have like paper mills now aren't just paper mills, they're actually power plants but with a paper mill attached to them nowadays. So down there they've got a monster power plant which is gas turbines and you know, 2 other sort of waste gas processes, all generating power. Now what they did, they got a deaerator which they stuck on the roof. It seemed a great place to put it because it'll keep it nice and cool. But the only trouble is the deaerator was radiating 90 decibels. And 90 decibels went out all the way across the area, and within a week the phone calls started, the letters started. So now they've got a major problem. What can we do? But the problem is here, the problem is now. So the first thing they started was like, can we change the valves? Yes, we can change the valves, but we might need bigger valves now because we've got to get the velocities down in the valves, and the valves are on 12 weeks. So next problem, what else can we do? Let's lag it. So then they lag everything, put loads and loads of acoustic lagging on, cost a fortune, still didn't bring the noise level down. So then they went down to silencers, to put silencers on there, which was like another way of getting the noise down. That was 30 grand just for the silencer as well as all the installation. So because of a mistake that was made at the front end, the costs were astronomical afterwards. So where you can, always make doubly sure you're going to treat it at the front end, because anything afterwards is going to be terminally expensive. What you can do as well on here, we mentioned the pipe schedule on their thing, so typically it's 2 dBA reduction per schedule change, so 40 to 80 is 2 decibels. If you look at your insulation, it's 5 decibels for acoustic lagging or 3 decibels an inch for thermal lagging, all of which will actually help you, you know, get where you need to go. Here are some of the trims you can actually use within the valves. So within ball valves they have these special baffle plate mechanisms with loads of little holes in. The idea is that you're actually introducing friction. Friction absorbs the energy, energy reduces the noise. So it's quite straightforward. On this, if you like, the flow will come in and it will have to fight its way through all these baffle plates and holes, absorbing energy and just reducing the pressure. And then downstream, occasionally you'll put what we call diffusers, which are these sort of you know, tubes with holes in, and then baffle plates with holes in. Now this is what goes on in a rotary valve, but in a linear valve you have the multi-stage trims, which are going to be all these trims with all these little holes drilled in. You know, very expensive to produce, you know, very high spec engineering. And then you can put attenuator plates, which is like an orifice plate with loads and loads of little holes in there. Next one is going to be your flashing or your cavitation. Now this one is, you know, whereas the noise is, you know, expensive, the cavitation is extremely damaging to things. So you need to avoid this like the plague, because valves will disintegrate within days if you don't treat them. So what you've got here, you've got your pipe, and in the middle here we've got an orifice plate which represents the valve. To pass the flow on a valve, basically what will happen is the flow will come in, and where the pressure drop occurs, you actually get a change in state where the flow accelerates as it goes across the trim. This point here is called the vena contractor within the valve, and at this point, if you like, what happens is you get a change of state taking place inside the liquid, and the change of state is the actual pressure inside the line will reduce dramatically. Quite often it will drop below the vapor pressure of the liquid, which is where you get your problems. So here you've got the liquid coming in. It's at this point, if you like, it's at pressure and it's liquid, so the flow will come through. As the pressure goes through the valve, it drops, and then it drops quite often below the vapor pressure. So inside the valve you've now got vapor formed, so you've actually got little pockets and bubbles in there of all vapor, which is the cavitation. Now if the pressure is allowed to recover, which quite often it has to do in the process to get the pressure back up again, it exits the valve within what we call cavitation, which is, I'll show you in a slide in a minute, which is very damaging. On the other hand, if you're dropping straight out to an open tank, it's going to change itself to flash, so it will stay in a vapor phase, so you'll end up with a very wet steam coming out of the valve, which can be extremely erosive. So both of them are as bad, but the flashing can be accommodated within the valve. You've got to be very, very careful with the cavitation. Now this shows you what happens. Here you've got your vapor bubbles formed inside the liquid, and then what happens is as the pressure recovers on the outlet of the valve, these bubbles will actually implode. But when they implode, they release a massive pressure, so you get 104 megapascal shock wave taking place actually from each of the bubbles as it implodes. Now, if the bubbles are contained within the flow stream, it doesn't cause that much damage. But of course, the liquid is going to be all around the inside of the valve, so where the bubbles implode anywhere near the metallic surfaces of the valve, then these bubbles will literally rip chunks out of the actual metallic structure of the valve. So you're going to be talking, as I say, 7 days and the valve will be trashed completely, throw away. So you don't want that sort of thing. Now, we had a very clever guy working for us some years ago called Joni Poitzler, and as his doctorate, he developed a way of predicting how cavitation was going to be. Because cavitation is a bit like a black art. If it's got it, people say you've got to avoid it. But the reality is, if you think about your cold tap at home, you open your cold tap, it's banging and crashing. That's actually cavitation, but your tap doesn't collapse. So what we found was, he found that there was a relationship between noise and the aggressiveness of the cavitation. So by making sure that your calculations are within the noise levels, then you can predict that you're going to get some level of operating capability within the valve, even though it is cavitating. Because quite often, the cost of an anti-cavitation valve can be horrific. So if you can tolerate it, then tolerate it. So here you've got different sizes of valves, and then you've got different noise levels that you can sort of work up to and still get a reasonable life out of the valve. So those are the relationships he's got. Now, cavitation is a bit like electricity. You know it's going on, but you can't see it because it's contained inside a metallic valve. Now, over in Helsinki, we've got the Finnish Flow Labs, and one of the guys came up with a great idea of sawing a ball valve in half. So basically what he did, he'd got a ball valve here and he sawed the thing in half, and then he bolted on a glass frontage. So now you've got a valve here where you can see what goes on inside the valve as the process is going on. So here you've got just over 4 bar liquid coming in, and at the outlet you've got 0. And you can see a fog here. The fog is actually the bubbles of all the cavitation exiting the valve. So we don't run this obviously for long times, it's just for a demo, if you like, while visitors are in the Flow Labs. But you can actually see what's going on inside here. And a party piece they actually do is they unscrew, they've got a drain plug in the valve, so even though you've got 4 bar on the inlet, they unscrew a drain plug and nothing comes out because the centre of the valve is under vacuum where the actual vena contractor is. So it's quite, an unusual thing to see that happening where you've got positive pressures but no liquids exiting the valve. And then here we've got one of the baffle trims that go inside the ball valves. You can't see them, but these trims are full of all drilled holes here. And now what you're doing, if you like, you're reducing the pressure in stages, so you're never actually reaching the point where the cavitation exists. So here you've got 4.5 bar down to 0, and you can see there's no vapor bubbles formed on the outlet. So you can actually see what goes on inside the valves. Now within your rotary valves, you've got technology of these baffle plate systems. There's various manufacturers that do them. And the way they're working, if you like, is that the baffle plates will go in here with all little holes drilled in. And the way it works is it actually reduces the pressures in stages. So instead of dropping below the vapor pressure, you're coming down in steps and not actually creating the cavitation. So quite a successful way of doing it. It has limited capabilities, whereas the glow valves have the capability to stand 160 bar pressure drops. The rotary valves won't do that. But for a lot of environments, it's quite satisfactory to get you through there. Now here's where you start to get into the sophisticated trims, if you like, for your glow valves, because you've got all manner of multi-stage trims available. So here's the first one, which is what we call a single stage trim. Now the single stage trim is actually a bit of a fudge, because what happens is that cavitation still exists, but where you've got all these little drilled holes in the cage, they're like jets, so they actually direct the flow, direct the cavitation to the core of the valve. So the cavitation exists in the core of the valve and then collapses before it actually gets to any of the metallic parts of the valve. That's the theory. I wouldn't always say it works, so be very careful if you've got anything on the single stage trims, because you might think you fixed it but you haven't, if you know what I mean. The next ones you go to is what we call multi-stages. Now here we've seen a microform trim, because on the multi-stages you've got the options of having full-size trims or microform trims. So this trim design here is the old terminology of what's called cascade. So basically what they do is they machine all annular rings around the trim, and so basically what you're doing as the pressure's going through, it's having to fight its way through all of these little annular rings before it escapes. It's just a machining on the trim, but when you sort of have a single stage trim and then this, it will allow you to take quite high pressure drops on small size valves. When you start getting into the bigger size valves and the bigger flows, you need to go to multi-stages, and what will happen then is you'll have cages which are going to be constructed for either 2 sleeves or 3 sleeves, and the idea is if you're building in all different kind of friction restrictions as the flow's coming through, it has to expand and contract and fight its way through. You're just adding friction, absorbing the energy. And then we've got labyrinth trims, which I'll show you on the next slide. Anybody done any work on labyrinth trims, labyrinth technology? Okay. Now, with the trims, if you like, they're all capable of doing certain things, so they're working in certain levels. And it's all down to just how much friction you can actually build into the trim to absorb the energy. Now, with the labyrinth trim, basically what you have series of plates. The plates will have all different profiles cut in, so it's actually like a maze profile. So as the flow is going through, it's having to change direction umpteen different times. And what they do with all of these stacks, they assemble them into all of these plates, they assemble them into what they call a stack. And by that, if you like, now you've got what looks to be a cage, but the cage is now made up of all these different ports and profiles. So what you can do here, you can see you can have a flow coming in and it's changing direction all the different times. I know in our trims, we do a trim where you can actually change the flow direction 300 times in one trim. So it allows you then to absorb large amounts of energy. But the downside is, if you like, as you're building in the friction, you're reducing the capacity, so you end up with bigger valves, bigger trims. So you need to have these unusual valves like the angle valves again. This trim you've got here is CCI drag technology, so their way of doing it is they spark erode their profiles into the discs. The same process, if you like, where you're adding all these multi-trims and multi-stages. It just means then you're doing it in a different way. Now what's neat with this sort of thing is you can actually design, design the trims, if you like, here. So here, if you like, you've got an application where you've got a labyrinth trim at the base and then you've got a normal multi-stage trim at the top. Because quite often with your applications, an example I will give you is condenser level control a deaerator level control on a power station. If the power plant is a continually operating plant, then everything's always at a static load. It's great. But nowadays power stations are cyclic. Most of them are all these gas turbines, so they're coming up and coming down. So what will be happening is on low load you'll have very high pressure drops across the valve. Hence you'll need for the massive anti-cavitation. But then when the plant's online, the pressure drops are then minimalised, so you only need a small amount of anti-cavitation. So you can, build and choose. Now, one of the things I like to point out to people when we're talking about these valves is that quite often people think of control valves as being relatively simple things. They don't sort of rate them as anything special. But if you use a power plant as an example, the last job I was involved on was a plant called Guangdong, which was in China. This was when I was at Fisher, and it was, I think they had 6 990 megawatt sets. Now, from the point of view of the power, that's fine, but the reality is you have to put turbine bypass valves in. So those valves are globe valves and they have to tolerate 996 megawatts as the valves are in operation. So whereas you think of the valve as being something simple, when you add the context it's got to cope with all of that energy and all that power, then it just gives it a slightly different meaning. This is just a quick picture now showing you what cavitation damage will look like. It's like a cinder effect where you can see all the bits of metal will be ripped out. This is where you need to start to put your specialist trims in there. On the other hand, if you've got a flashing damage, the flashing is more like an erosive application, so it's now ripping scallops out of the trim, so it's wearing the trims away. So that can be rectified by hard face trims. They'll tolerate that. Or in the where you've got severe flashing, then use the angle bodied valves where you're flashing into the outlet. And on the Guangdong one, we had massive flashing on there because it was they were dealing with very low pressure condensate and steam, so everything was like wet. So they ended up putting special baskets at the base of the valves to absorb the energy of the flash as it was coming through to stop it wearing all the pipework away. That ends the presentation from where we are there. Now, when I first started with Metso, coming from Fisher if you like, the world at Fisher was all globe valves, but then when I arrived at Metso it was all rotary valves. So I had to try and find a way of showing people just what you could do and what you couldn't do versus globe valves versus rotary. So I started to put a database together of various applications and processes where I could actually compare the two. But since I've been doing these presentations, I've kind of adapted it now because Metso manufactures all the valves. So now, if you like, you can use this tool as a good, easy guide, so you can pick and choose what valve is going to be the best for you. So along the top here, you've got all the different kinds of valves. So you've got your traditional top and bottom guided valves, then you've got your cage guided valves, rotary plugs, butterfly valves, ball valves, segmented ball valves, contoured V-ball valves, ceramic valves, plug valves and line valves. And then we've got all the different applications going down. I've got 2 lots of these which are on the presentation. And then what I've done, I've actually identified them all under the merits. Now, this isn't designed to guide you to Metso in any form. It's just a tool that I now use for education purposes. So for instance, if we're going down here on some of the applications, so here we've got flashing. So the traditional top and bottom guided valves are down as not being too good, whereas the cage guided valves, because of the designs on those, they're not going to wear out quite as quickly. They're down as A. And then if you're looking at a butterfly valve on flashing, that's down as B, because you're likely to get localized wear and tear on a butterfly valve. So now what you can do, you can look through your applications you've got here, and then you can check and find out which valves are going to be the best for the application. Because each of the valves have got the merits, the key factor is for you guys as engineers to pick the valves which is the best valve for the job. So what it does now, it gives you the opportunity now, instead of saying, well, I've always used these, I'm staying with these, even though it breaks every 2 years, you can now say, well, consider some different options. And it gives you all the choices as to what you want to do. So you've got 2 of these things now with all the different applications that I tend to come across. But obviously, myself, I've been in the business now for 37, 38 years. Colin? You? So Colin's catching me up, but obviously much younger than me. So if you do need any help on specific applications, then we'll give you the information, we'll give you the guide, but it won't necessarily be the big sell. It'll be more trying to ease you through the process. Because not everybody uses Metso valves. It's all about picking the right valve for the job. So that basically finishes my sort of show for you, gents. So any questions?
You haven't mentioned shut-off classes.
Right. It's funny you should mention that. Glasses. 1 second.
Used to be in the industry, but
I didn't know whether you'd want to see this, so it's here, but it's hidden. No, 1 second. Right, what are we doing with it?
relief also as well.
Okay, now you've got all your different shut-off classes. I mean, typically they've always been rated in 2 forms. When you're looking at control valves, they tend to be rated in the ANSI format. So ANSI Class 2, ANSI Class 3, ANSI Class 4, ANSI Class 5, ANSI Class 6. Now, on the older, cruder control valves, then the shut-off classifications were down as ANSI Class 2. And ANSI Class 2 is going to be a quantifiable number which is based on a CV. But when you're looking at the more modern control valves, they tend to be Class 3, Class 4, Class 5 and Class 6. Now, depends on what you want to do with it. The normal shut-off class, if you like, for a control valve will either be ANSI Class 3 or Class 4, because most control valves, if you like, they're designed to leak. However, there are processes where you might want your control valve to be a shut-off valve as well as a control valve. I mean, if I look at, you know, reactor steam or reactor heating valves, if you like, if you've got a valve which has got a leakage rate, it's continually passing the heating media through to the reactor, which cooks the reactor and then damages whatever's inside, because the key factor on reactors is keeping the internals clean, whereas if you're baking whatever's in there, you end up with residues and dirt, and it's a nightmare to clean. So one of my colleagues came up with this unusual sort of system where it's worthwhile thinking about what you're actually asking for, because there is a cost added to the shut-off classifications. So on a normal glow valve, as I say, glow valve is going to be ANSI Class 3, ANSI Class 4 for a normal glow valve. If you want to go to ANSI Class 5 or ANSI Class 6, you end up paying for either somebody to do specialist machining to make it tighter, or fitting special seals around the trims, or you'll have to go to soft seals, which then become more and more expensive again, and then you'll be in you know, a problem area. So what one of my colleagues did, he came up with this wonderful idea of sort of actually putting the leakage rates into context. Because I had one of my customers some years ago where he demanded that one of my control ball valves be a Class 5 shut-off. And it cost, if I remember correctly, it was about 15 years ago, it cost about £4 to get this valve to as tight as he wanted it. And when the process engineer came up, he said, what the hell have you done that for? It doesn't matter if the valve leaks. So basically what we've done here, if you like, you've got a sheet here which we call it making sense of leak rates. And what it will give you, it will give you the amount of liquid you know, it will take to fill a pipe within a given time. So you can actually then make an estimate for the different pipe classes. You can estimate just how much a leak means, because people ask for these numbers without actually understanding what these numbers mean. So what I intend to do, I'm going to send this out to Colin in a PDF format. So I'll add this into the PDF so that you guys have got it. And then once again, it's a tool which will give you a guide again, because you know these numbers are there, you know what the basics are going to be, but don't always ask for a tight shut-off if you don't want it, because there will be a cost. Now if it's a butterfly valve or a ball valve, you're going to get it whether you want it or not, because those are going to be tight shut-off. But if it's a normal control valve, then it's ANSI 3, ANSI 4 and occasionally ANSI 5.
Do you have equivalent tables based on the European standards, DN and NP?
I don't have them, but we can probably work something out if you needed it.
I mean, this is very much an oil and gas
we get into this.
Used relatively infrequently elsewhere.
Yeah, we get in this weird world where half of our valves are spec'd out in the you know, the European standard, and the other half's in ANSI standard. So it gets very confusing for me sometimes. Because you tell somebody just how tight it is, it's like rate A, and they say, what the hell's rate A, you know?
Yeah.
But if you tell them it's ANSI Class 6, then, you know, they know exactly what it is. Of course, ANSI Class 6 is like bubble tight.
A lot of people, when they're designing processes, think if they can get a tight shut-off control valve, they can save money because they don't have to put an emergency shut-down valve. And it's very rarely the case. If you put a valve in that's capable of doing control and treat the shutdown as a separate entity.
Yeah, I tend to pick and choose. As I say, if I'm looking around a chemical plant with reactors, then I will use the control valve to do the isolation during the process. Because quite often the processes are like profiles. You know, they'll be heating, cooling, and they'll be going through a cycle profile. However, they'll still always add a secondary isolation, because you know, if this thing, the plant is going to be offline for 6 weeks, they don't want anything going in through the reactors because it just does damage. But if you're looking at the butterfly valves, especially with the triple offsets, you can get reliable tight shut-off as well as the control with the butterfly valves, because of the triple offset design. They're self-cleaning, the trims on those.
But you can't get it with 86 inches.
Sorry?
You can't get it with 86 inches.
Oh no.
It has to have a bladder in it, which when the valve closed, the bladder inflated all around the
Yeah.
of the valve
Yeah.
and outside of the valve.
You don't see those very often. I've come
No.
across those before. Yeah. They tend to be sort of. I see those a lot on hygienic applications where you can you can clean everything out.
Yeah, this was a thermal oxidizer rather than a acrylonitrile plant.
I haven't seen anybody building any of those for ages now. They used to be big business about 15, 20 years ago. Everybody was having them, weren't they?
Only got them in China now.
We manufacture in China, so we're all right. Any other questions, gents?
Right.
Now, if it's of any use to you, as I say we've got these catalogues, well they're not catalogues, they're manuals, which is our control valve manual, which has got a lot of the information that we've talked about today. Any of you that want to do valve sizing or anything, there's quite a nice valve sizing program in the CD catalogues. And there's some notepads and pens if you haven't already stolen them. Thanks for your time, gentlemen.
Well, just before we go, gentlemen, I'd just like to say thank you, Phil. I certainly found that very interesting. I've known a lot about control valves, but not everything about control valves in my career. I hope you found it as interesting as I did, and say thank you to Bill in our usual fashion.